Hello! In this video, we'll talk about correlation and how you can use it to measure the relationship between two numerical variables. So let's get started. In statistics, correlation measures a very special type of relationship. And to illustrate what we're looking for, let's start with an example. So the data set that we're looking at has to do with revenues from nursing homes. So nursing homes are especially concerned with the cost of healthcare and balancing these revenues. So the nursing.csv dataset contains information that was collected from a random sample of 52 small hospitals in the state of New Mexico. Variables in this dataset include the number of beds, number of inpatient days per month, number of all patient days per month, monthly revenue from patient care, monthly salaries from their nursing staff, expenditures on maintenance, and whether or not the hospital is located in a rural area. So let's take a look at just a simple relationship here. Maybe the number of beds is a good proxy for the size of a nursing home. Looking at this scatter plot, I have the number of beds plotted on the x-axis, revenue collected from the nursing home on the y-axis, and we can pretty clearly see that as the number of beds is increasing, so is the revenue that the nursing home is taking in each month. So it looks like there's a pretty clear relationship between the number of beds and the revenue. It's also a pretty linear relationship. We can imagine where a straight line could be dropped in the middle of this relationship. Because we can see that clear relationship, there might be a strong correlation between the number of beds in a nursing home and the revenue. So let's talk about what correlation represents. Correlation is a measure of the strength and direction of the linear relationship between two numerical variables. We'll represent correlation using the letter R, depending on which textbook or reference you're using. This can be either an uppercase R or a lowercase r. I tend to prefer the lowercase r just to avoid the confusion between R, the correlation, and R, the programming language. Correlation is what we refer to as a bounded measure. So there's no units for correlation. It's simply constrained to be between -1 and +1. Now, if we have a positive correlation between two variables, we say that there is an upward linear trend. As x is increasing, so is y. Negative correlations indicate downward trends. So as x is increasing, y tends to decrease. If there's no correlation, then there's really no clear pattern or relationship between the two variables. Now, depending on where we fall on this +1 to -1 continuum, points may be sort of scattered away from the line, or they may be very close to the line. So the scatter plot in the middle here represents a situation where there's no correlation. There's no clear linear relationship. As we move away from 0, either positive or negative, we see those points start to fall closer and closer and closer to a straight line. When we get to a perfect correlation of either r equals 1 or r equals -1, all of the points are falling exactly along that straight line. Now, correlation can be deceiving, and there's an example that I like to use at this point that's pretty classic in the statistics literature. This data is called Anscombe's quartet. So we actually have 4 scatter plots here. All of these have the same correlation, and it's a pretty strong one too. It's 82%, or 0.816. The only relationship, or the only graph, however, that I would say does exhibit a linear relationship is plot number 1. As x is increasing with these orange dots, y is also increasing. The rest have some problems. So plot number 2 has a very clear curvature to it. This definitely does not represent a linear relationship between the variables. Plot number 3, all of the points are actually perfectly correlated, except for one. There's an outlier at the very top of the data set. Plot number 4 is the same idea, however, there was no correlation until the outlier came along. So we can have data sets, or we can have variables that have a different type of relationship, say a quadratic relationship, and still have strong correlation. Or outliers can come along and either, in the case of number 3, decrease the correlation, or in the case of number 4, introduce a correlation that wasn't there to begin with. We can calculate the correlation between any two variables or any variables in a data set in R using a function called core. So this function takes in a data set and calculates the correlation between every pair of variables. X is perfectly correlated with itself, so it has a correlation of 1. Y is perfectly correlated with itself, so it has a correlation of 1. X and Y have a correlation of negative 0.06. So this data set has a very close correlation to 0, so we would expect that there's really not a linear trend. And you're right to expect that there's not. But there is still definitely something happening with this data set. The points are not linearly related, but they do form kind of a cool dinosaur shape. So there's definitely something to be discovered in the plot of this data set. So correlation alone doesn't tell the whole story. Always plot your data along with calculating your correlation. That way you'll know whether those strong correlations actually are representative of a numeric or a linear relationship, or whether there's something that hasn't been discovered with a weak correlation. So with that, let's look at some more examples of correlation and plots that go along with them. So when we're working with numeric variables, it can be really helpful to look at all of those pairwise correlations using that same core function. However, there can be a problem with doing this. This correlation function is only expecting to see numeric variables, which makes sense because if we have a linear relationship, X and Y are the two input variables must be numeric. The nursing dataset has an extra variable in it that's not actually numeric. It's this rural variable. So what do? Well, we remove it. So I can use the select function here to remove this variable. So writing select minus rural removes that rural variable from the dataset. I can then calculate the correlation and then plot that correlation using something like a correlation plot. So here's what gets produced. On the diagonal of this plot, we see some very big dark blue circles. These are correlations of exactly 1, which makes sense because these diagonal elements are variables correlated to each other. So beds should be perfectly correlated with beds. The bigger blue circles indicate strong correlation. So there is a very strong correlation between patient revenue and the number of beds. There's a pretty strong, but not as strong, correlation between patient days and the number of beds, patient days and inpatient days. There are also some negative correlations indicated in red. There's a negative correlation between the number of all patient days and facilities expenditures. So if we have fewer all patient days, we would be spending more on our facilities. There's also some negative relationships between nurse salaries and inpatient days. So certainly those are things that we would want to investigate further in this data set. The downside of this core plot approach is that we haven't actually plotted these relationships. So another option comes from the performance analytics library, and it's a function called chart.correlation. So let's see what this code does. Now this function calculates a lot of things for us at once. On the diagonal entries, we have histograms of each variable. So we can see how beds are distributed, inpatient days, all patient days, patient revenue, nurse salaries, and facilities expenditures. On the lower half, we can see the actual scatter plots of those relationships. So for example, there is a somewhat strong linear relationship between the number of beds and the number of inpatient days. Flipping this, looking at the other side of the diagonal, that exact correlation is 0.57. For inpatient days versus all patient days, there's a pretty strong linear relationship. The exact correlation is 0.81. So on the upper half of this plot, you get the exact correlations. The font is scaled to match the correlations, so the bigger the font, the more those correlations are going to jump out at you, whereas small correlations will have a pretty small font, so they'll kind of disappear into the background. The last thing to notice on these plots is the red asterisk. This function is also simultaneously testing whether or not the correlation is significantly different from 0 using a hypothesis test. These asterisks just indicate how small the p-value is. So the more asterisks, the smaller the p-value. So let's take a look at another data set. This data set is called the Health Evaluation and Linkage to Primary Care data set. This is a study that was done using adult inpatients coming out of a detox unit. The goal was to help them find primary care providers or regular physicians, with the idea that regular doctor's visits would help them stay clean from using substances. So we'd like to look at the numerical variables in this data set to see which ones are strongly correlated. First, I'm going to show you what this data actually looks like. So any variables that come any data sets that come prepackaged in R, we can look at or view using a question mark. So I'm going to go to my R console and here type help RCT. When I do that, I get the documentation, or I get a list of all of the variables in this data set. So we have 453 observations. Some of these variables are clearly numeric. Age, for example, is a numerical variable. Some are clearly categorical. So whether they've used a substance since leaving detox, that's a categorical variable. I'll use the select variable to choose which variables to keep as being numeric in this data set. There's no minus sign in front of any of these, so I'm keeping these variables, not getting rid of them. Once I plot the correlations, I see a lot of variables that really aren't related, but some are. There's a relationship between the average number of drinks and the maximum number of drinks. There's correlations between something called I1 and I2. And then there's a strong negative correlation between something called MCS and something called CESD. So I'm going to look through the R documentation and see what those variables are. We'll start with CESD. This is a measure of depression score, so higher scores indicate a patient who is more depressed. MCS is a mental component score, so lower scores indicate worse mental health. So someone with a high depression index probably is in pretty low mental health, thus the negative correlation. I1 and I2, these are the average number of drinks consumed per day in the past 30 days. This is measured at baseline, so at the beginning of the study, combined with maximum number of drinks. Correlation there makes sense too. One caution, when your data set gets reasonably large or gets fairly large, it's difficult to use the chart correlation approach. Now, I would recommend only using this function if you have, say, 5 to 6 variables maximum. Certainly there's too many variables here to really tell what is going on. We can see, though, that there are some linear relationships popping out. There are some strong correlations popping out. It's just difficult to see what those variables actually are. So let's take a look at one final example with correlation. This is a study on nutrition. So researchers collected data on 16 variables from 315 subjects to try to see if there were relationships between diet and blood plasma levels of two elements, beta-carotene and retinol. We might want to know which variables are strongly correlated with blood plasma levels of beta-carotene and retinol. We'd like to know the nature of the relationship. So are they positively or negatively correlated? So first, I'll select out only the numeric variables. Again, if your data is all numeric to begin with, you can skip this step. I'll then plot the correlations, here I've added something in this correlation function. I've added an option to use complete observations. There are missing variables or missing information in this data set. Anytime you have missing data or NAs, you will want to add this complete observation helper. So looking at this correlation plot, there are a lot of variables that really don't have much correlation. Some of these in the middle do. Some aren't surprising, so there's certainly a correlation between calories consumed and fat consumed. There's certainly correlations between calories and fat consumed and cholesterol. Specifically, we wanted to know about beta carotene in the blood plasma. Doesn't really look like it's strongly correlated with anything. Similarly, retinol levels in the blood plasma, not really correlated with anything. Finally, we could use that chart correlation approach. Beta plasma and retinol plasma are down along here. Not really seeing many linear relationships. These correlations are all pretty tiny. They're difficult to read. That's on purpose because they are such small correlations. So we will stop here with this overview of calculating correlations and working with correlation in R. Next week, we'll talk about regression. Have a good day.